Hello and welcome to this video about matrix data structures. In this video, we'll learn how to write a computer program to find the square root of a matrix in Jordan canonical form. This is important because then we'll be able to find the square root of any matrix. Since not every matrix is diagonalizable, then being able to find the square root of a diagonal matrix won't help us to find the square root of every matrix. But since every matrix is Jordanizable, then finding the square root of a matrix in Jordan canonical form will help us to find the square root of any matrix. The entire process can be done in a computer program. In this example, this is how to find the function f applied to a Jordan canonical matrix. It can be split into Jordan blocks, and all of the derivatives of f need to be calculated for each block. If the block is of size n, then all of the derivatives of f need to be calculated up to the n-1th derivative. In this case, it has size 3, so all the derivatives up to the second derivative need to be known. And these entries will have to be divided by their corresponding factorial values. Here is another example. This matrix contains a Jordan block of size 4. So the third derivative needs to be known. This matrix is made up of one Jordan block of size 6, and the fifth derivative needs to be known. And this is the general form of a Jordan matrix, being one whole Jordan block, and its corresponding matrix that's equal to the function applied to this matrix. So this is a quick calculation of the square root of a Jordan matrix. We need to know the derivatives of the square root function, which is a little bit messy. We need to make up a table so that we can calculate them for matrices as large as we desire. We can calculate them in advance by hand, or we can use a computer program to do it, which we'll do later in this video. So the first step is to convert a Jordan matrix into a table of values, which can store this matrix effectively. We can use a function to test whether or not it is in Jordan canonical form, and then convert it into a table of values. We can split this matrix up into these Jordan blocks as shown. The diagonal entry lambda 2 is a purely diagonal entry, but can be stored as a block of size 1. The computer program will calculate the storage of these blocks by the location of the 1s and 0s in the superdiagonal. This is how we'll store this matrix in this table of values format. We'll store the value of the diagonal entries, which will be the same for the entire block. Then the starting position of each block as they are found in the matrix. Then the size of the blocks. So now to write a function to convert this matrix into a table of values. We'll declare the function and then reset these indexing variables, which are index variables to the row in this matrix and to the table that we're creating. And we'll make a loop to go through every row of the superdiagonal and ignore the last row because the superdiagonal has no entries in the last row. We'll get the locations and values of elements in the diagonal and superdiagonal corresponding to the indexing variable I. We'll make another loop to go through every entry in the superdiagonal while we're still in the block. That is, when the superdiagonal entry is still 1. The variable k will be the size of the block. We'll increment the row number I as we descend through the block and get the value of the next element in the superdiagonal. We'll increment the size of the block here. After we finish being in this loop, we'll set the table information here. We have an interesting formula for the start of the block. We could have just as easily have used a separate indexing variable for it like m. So now we'll increment all of the variables here to look at the next matrix and table entries and the indexing variable to prevent infinite loops. And because the last entry in the diagonal doesn't have a superdiagonal entry across from it, we'll have to work with it separately. We'll get the value of the last element together with the superdiagonal entry directly above it. And if this superdiagonal entry above it is 0, it will be its own block and be stored as its own block. And then we'll increase the number of blocks in this table. Otherwise, if the superdiagonal entry above it is a 1, then it's part of the previous block, and will increase the size of the previous block in the table. And finally, we'll store the number of blocks in this global variable. And so now we've finished converting this Jordan matrix into a table of entries. So now to look at how to create a table of values so as to calculate the ith derivative of the square root function. We'll start by expressing the function in indice form, with x raised to the power of a half. We can get the first derivative by using the exponent rule. We can then get the first 5 derivatives using the exponent rule and the multiplication by a constant rule. Then we can generalize this derivative by looking carefully at how all of the constants in the function behave as we keep finding the next derivative. We can use this equation to find an unlimited number of derivatives of the square root function. We can store these numbers in a table given by these constants. The num array, which is short for numerator, corresponds to this part of the derivative. The den array, which is short for denominator, corresponds to this power of 2 in the denominator of this fraction. The power array corresponds to this number which x is raised to the power of. We can calculate the coefficient of x in which we gather all of the constants together that are multiplied by x. This coefficient is equal to the numerator and denominator that we've just calculated, and then divided by the factorial of I, which we need to do before inserting it into the matrix. I is the indexing variable, and it's not the imaginary number here. So we can calculate the value of this coefficient from this formula, or calculate it immediately, not using these numbers, since these numbers num, den, and fact can grow extremely large. Now to write a computer function to make up a table of values that we can use to calculate the ith derivative of the square root function. We'll firstly declare the function with all of its internal variables. We'll calculate the special case for when I is equal to 0, because these numbers are calculated differently from the rest of the entries. We'll initialize these values before we enter the main loop. We'll make up the main loop here to fill in the rest of the entries in the table. We'll enter the values into the table here, starting from I is equal to 1. They can be calculated according to a fairly regular algorithm or method from now on. We'll calculate a special factorial table as well. Since the entry in the denominator is a power of 2, we need only multiply this entry by 2 for every iteration of the loop. And we need only multiply the numerator variable by the next negative odd number for every iteration, because this is what we need to do according to the theory. And we can calculate the coefficient by multiplying and dividing it by these numbers for each cycle. It's best to do it like this because the numbers den and num may grow too large for the computer. There will be some loss in accuracy as we do it like this. Maybe we should use numbers with a far greater accuracy, like JavaScript's big number type. We can also divide this coefficient by the factorial here, and calculate the value of the factorial for the factorial table. We can calculate a second value for the coefficient from these variables we've just calculated, to compare it to the other coefficient entry, to verify that it's correct. And then finally, we can set the size of these tables here by setting the values of these global variables. Now to make a function that can use the Jordan blocks table to create the square root of the matrix. We'll make a function with 2 loops for each Jordan block. The first one moves across the block, and the other one moves down diagonally. In this first stage, we'll fill in the diagonal with the square root. Then we'll fill in the superdiagonal with the first derivative of the square root. Then we'll fill it in with the entry for the second derivative, and we'll have to divide the second derivative by the factorial of 2, and then place it into the matrix along this diagonal line, so it fits into the block square. And finally, we'll place the value according to the third derivative here. We could just as easily have filled out a Jordan block that is 100 elements wide. So now we have to use this function to use the values from the square root table and Jordan blocks table to calculate the square root of matrix A. we'll declare this function with all of its internal variables. We'll set up the matrix B by setting its row and columns variables and setting it to be the zero matrix. We'll make up a loop to go through every Jordan block that we've found in matrix A, and that's in the Jordan block table. We'll get all of the different attributes from this table and get the square root of the diagonal element straight away. We'll make up a loop to go through every derivative that we need to fill the Jordan block. Then we'll get the coefficient and power of x that we need to put into the locations in this matrix. This loop can be thought of as going across the matrix to the right. And then we'll fill in the matrix with values according to the Jordan block. We'll put in each entry that we find as we go diagonally through the Jordan block in a direction going right and down. This is the block in B that's in the same location as the block in A. And so this gives us the completed square root of the matrix A in Jordan canonical form. Now we can put all of these functions together into this one function. We'll assume that we've already called the function that creates the square root table earlier. We'll declare the function with all of its internal variables. This matrix must be a square matrix. And this matrix must be in Jordan canonical form. I've made up another function to do this in a previous video. We'll get a table of Jordan block values from the matrix A. And then we'll use this table to get the square root of matrix A and put this square root into the matrix B. Now to create the square function, it multiplies B by itself and places this value into C. I've explained multiplication functions in another video too. It's good to have a look at it here. It contains 3 nested loops. It has to be this complicated. This function compares A and C and tests whether or not they are equal or equal enough. In the part circled in red, this gives the accuracy of how equal they have to be. Any 2 entries have to have not more than this difference between them. And now for the testing function. We'll declare the function here. We'll create the square root table here. It only ever needs to be done once. We'll create a loop to test 100 matrices here. This function creates a random 7x7 matrix with a single Jordan block of size 2 or greater. We'll get the square root of A and place it into B. Then we'll square this square root and test to see whether it is a square root by comparing it with A. If it isn't a square root, we'll return an error and print out the value of all these matrices. We'll print out a finished message at the bottom here to let us know that we're finished. This method can easily be adapted for any function, like for logarithms, exponentials, sines and cosines. We'll be studying these different functions for Jordan canonical matrices. It's only necessary to change the function derivative tables. So I hope that you have found this video to be helpful, interesting and insightful. Please click like and subscribe if you did. Feel free to share this video. Please leave some helpful thoughts in the comments. And thanks a lot for watching.